Okay, let's finish up the unit by looking at sounds a little bit more closely. So I'm going to get you guys to take some notes because we're going to replace lesson 7 with some other stuff here. So sound waves, more details. So we're going to talk about, well, you know, what kind of wave is sound wave? Is it transverse or longitudinal? Which one? Sound? Longitudinal, right? So it just travels back and forth, is just a disturbance, and you need a medium. So longitudinal waves, you need particles to vibrate. So that's why you cannot have sound in a vacuum. Outer space can't have sound. Okay. What do you notice when you change the pitch? So last time we talked about how sound is transmitted, right, and received. So you're vibrating the air between the transmitter and the receiver. It hits your eardrum in your ear, hits the 3 bones, gets into your brain, and eventually record that as sound that you hear, right? So, but how does sound actually vary? So if you look at the different properties of wave, okay, let's say your frequency. If I change the frequency of sound, what would that actually do to the sound itself? And what about the melody of the sound, or the tone, right? The tone or the notes itself. So if you're playing music, the notes, what would that be in terms of the, is it V equals F lambda? So which one of those 3 properties of waves, which one of those 3 variables do you think would be, so here's the frequency, what would it do in terms of the sound? Would it change the pitch or the loudness? What do you think? So frequency has to do with the pitch, right? So if it's high pitch, what does that mean in terms of frequency? So if there's an increase in frequency, the pitch will be higher, right? And vice versa. The notes itself, which one do you think would be in this one here? Would it be the, well, it's not the frequency. Would it be the wavelength itself, or the speed of the sound? Make a guess. So you know it's not frequency, because changing the frequency changes the pitch. So when you want to change the notes, how many of you play a musical instrument? Or you can read notes? Guitar? Piano? Clarinet. Okay, so when you're changing, when let's say you're playing a C or a D, right? G, A, B, C, it doesn't matter what note you're playing. What do you think is happening here? Which one are you changing? The loudness. Okay, so if I play a G, for example, can I still play a G quietly? Can I play a G loudly? And I didn't change the note, right? So it won't be the loudness. Okay, so let's actually write down loudness as well, or the volume. Okay, so the note itself is actually the wavelength. So the wavelength is what changes, and it changes the notes. When you change the wavelength, it will change the tone or the note of the sound, right? Loudness would be the amplitude. So an increase in amplitude, an increase in loudness, right? It will be louder. So this is measured in decibels. Okay, so if you're looking at measuring the loudness of a regular conversation, that would be measured in decibel. Okay, so that's the loudness. So we looked at frequency is pitch. I should have switched those two. So pitch is frequency, notes are wavelengths, and loudness is amplitude. So when it comes to loudness, when it comes to sound waves. Oh, okay. Have you guys heard of beats? Okay, so in sound waves, there is a concept called beats, and it's some of the questions in your review handout ask about what is a beat, right? So if I get you guys to pull out the handout that says sound waves or basics of sound waves. This is the same one that you have, except this one is a bigger font. On the back of that, it says beats, right? So when you have two sound sources with different frequency, the resulting wave will vary in intensity or loudness, like the amplitude. The sound will come and go with the frequency that is the difference of the two source frequencies. So that is the beat. So when you have two different frequency that you're hearing, you're going to subtract the two. So let's say frequency. So frequency difference between two sound sources. It can have more than two, of course, right? So you can have many different sound sources coming to you, and the difference will be what we call beat. So here's an example. Let's say you have frequency 1 is 200 hertz, and then frequency 2 is 300 hertz. So then the beat will just be whichever frequency is, what is the difference between the two? 300 minus 200. This is absolute value because it doesn't matter which one you put first, right? And you're gonna get a 100 hertz frequency. That would be the beat. Okay. So that's pretty simple when it comes to calculating beats. Another unique characteristic of waves is what we call the Doppler effect. Doppler effect happens to both sound and light waves. So longitudinal and transverse. You get Doppler effect. Okay. Did you guys hear that siren that just came by? There was an ambulance, and just leave it a little bit. And just leave it like that up to my head. Okay, so then there was I can't remember if that's an ambulance. Can you guys tell if it's an ambulance, a police car, or a fire truck? Would you be able to tell if you're up there? Can you tell slightly different? Fire trucks tend to be, well, they're louder and it's a little bit lower pitch, right? And there's a little bit of tone as well, how they, the beat would be different. But anyway, when you hear an emergency vehicle, they exhibit Doppler effect. Do you know why? It starts to change in terms of pitch. And let's just take a look at something here. Okay, so here we have a car. Okay, so this is a car horn. This is a Doppler shift from a car horn. Okay, that was really short, but here we go. Okay, so car was coming towards you, and then it was in front of you, and then it was moving away from you. What do you notice? What changed? What changed? Okay, there's got to be more than one that changed, right? So pay attention. Here we go again. Okay, so what happened there? So what happened? Let's talk about the pitch. Okay, so we're looking at pitch, tone, and loudness, right? So what happened there? When it was coming towards you, was it getting louder? Okay, that was easy, right? Because when a sound source is coming towards you, it's gonna get louder and louder, right? because when it goes away, it gets quieter. That makes sense, right? But what do you notice about the pitch?
It got lower.
It got lower when it was coming towards you?
Well,
Or-
that's when it was like just in front of you.
Okay, so it reached, but what was happening when it was coming towards you? Was it going higher pitch or lower? Should we play that one more time? Okay, let's look at coming towards you first. Okay, here it is. Okay, what happened there? When it was coming towards you and then just before it got in front of you, what happened to the pitch? It got higher, didn't it?
Higher.
Here we go. See that? Okay, it was higher and higher, and then as soon as it got in front of you, it started to get lower pitch. So not just the loudness changed, right? So the loudness, obviously, it got louder as it comes towards you, okay? And then it got quieter when it was moving away from you. But the pitch was the one that was mainly affected, right? So when you're out there, you're driving or walking, and this is why it's actually not safe for you to be driving with your stereo very, very loud, right? With your radio cranked up so loud, because you may miss those emergency vehicles. And also, if you're walking, when you're crossing the street, I know last summer there was a very young 20-year-old woman that got run over on Sargent and Simcoe, and there was that was actually that it's a pedestrian with a light, and there's been 2 car accidents there, pedestrian car accident, 2 in 1 year. Okay, there was one person that was crossing, and you press the light and you see the blinking lights, right? So you go, okay, it's my right of way, I'm just gonna go now. Okay, but the person has headphones on, and you had headphones on, and when you turn on the light, that does not give you a force field that makes you safe to cross the street, right? Sometimes cars can't stop. Sometimes cars are not, drivers are not paying attention and they don't see you. And when you collide with a car, if a person collides with a car, you have no chance there. You're talking about a 2,000 kilogram piece of metal driving at whatever speed, and you with your fragile body crossing the street. So you gotta be mindful, okay? So walking around with your earbuds, your AirPods, is not safe for you, especially when you're crossing the street, okay? Just remind yourself that even when you're waiting for the light to turn to cross the street, especially in the winter, don't just stand like right at the corner. I always stand behind the post, just in case, because I actually know someone, a friend of mine, her sister got run over on Notre Dame by the independent jewelers there. It's a major cause of car collision. That's why they renovated that. I don't know if you guys know independent jewelers it's Notre Dame and Salter. It's not very far from here. Okay, there's been so many car accidents there. People waiting to cross the street, and cars can't stop, and they're pressed right up against the wall of Independent Jewelers building. So they said, you're gonna renovate your building and give it some room, because if you're standing right here, there's that building used to be there. So that was a very dangerous spot. So just be mindful. So if you're out there and you can hear the pitch getting louder and louder, okay, it's coming towards you, right? But the indication is also the pitch. So if it's getting higher pitch, that means it's coming towards you. You gotta pay more attention, right? If you notice that the pitch is getting like lower and lower and lower, you know that it's moving away from you. Okay, so that is called the Doppler effect. Okay, that happens with sound. So that's the one that we just heard, and I'm gonna take a look at what about light wave. Okay, so I just put here light waves also exhibit Doppler effect. So let's just write down something here. Sound waves, the frequency is the one that changes. Okay, so an increase in frequency, that means the source is going towards the observer, and a decrease in frequency, that means you're moving away. So the source is moving away from you. Okay, what about light waves? Well, you're not gonna hear it because it's light, right? But you're gonna see something. So look at the visible light spectrum, because we're talking about the visible light. only, because that's the one that we can detect with our eyes, right? We can also look at the whole electromagnetic spectrum, but let's talk about the one that we can actually see. So we have Roy G. Biv. That's the spectrum of visible light. So Roy G. Biv, red with being the longest wavelength, right? I'm not going to change the amplitude here. So it's getting more frequency right there. So violet is the one with the highest frequency, highest energy color. So if, let's say, you have a star, and that star is, say, yellow, like our sun, right? Our star is the sun, and it's a yellow sun. And let's say that you are now in outer space and you're moving away from the sun, like very far away. I'm talking outside the Milky Way. What do you think you would see? What would you see would happen to the color of our sun, which is yellow, if you're moving away? Now let's go towards first, because I wrote towards in the first one. So if you're moving towards this object and it's a yellow sun, what do you think will happen to the color? Will it change? So you have a yellow sun and you're now moving towards it, closer and closer and closer. What do you think would happen? See this shifting right here? So we talked about the change in frequency, right? Well, Doppler effect is defined as the change of frequency when an object is moving towards or away from you. The frequency will change. So in terms of visible light, if you sense that as a yellow star and you keep moving towards it, do you know what would happen to that color if you move towards it? Well, there will be an increase in frequency, just like with sound waves, right? So what color do you think it will become? It will actually become green, right? Except our sun is naturally yellow and we're so close to it that we actually see the real color. That is the color of our sun, and that is based on the energy level that it carries, right? Because you have a nuclear reactor in the core of the sun, and that's how much energy it's emitting, and that corresponds to the color yellow. Because we are in the solar system, we see the true color of our sun, okay? But if you have a person and you're observing a star, now we are here, right? This is actually what's happening. There are people out there who look at stars out there, and let's say there is a star that appears to be yellow to us, but we don't know if that star is actually yellow because we're not in their solar system. So let's say you have this yellow star, not our sun, okay, somewhere else, and it appears to be yellow, and then so we start moving towards it and it appears to be green. So then maybe that is the actual color of that star. Maybe it's blue, maybe it's violet, until we actually get into the vicinity where you're in the solar system, where you're actually orbiting it, then you won't see the true color. So this is what they're actually seeing, that if they look at a star, let's say Vega is the name of a star. Our closest star is we have Vega, we have Betelgeuse. Those are the stars that are in our neighboring, our neighbors, right? They're saying that the stars that they see are shifting towards the red light. So if they're looking at the yellow star, okay, and then they check again years later, they notice that exact same star has become orange. And this is what they're saying. If they see a blue star, okay, they keep monitoring that star, and years later that blue star appears to be green. And they're very precise. They're not just looking at light that we can detect. They're using special telescopes that can detect the frequency that corresponds to that particular color, because every color has a frequency and a wavelength. If you change that wavelength, you're changing the tone of that color as well. You know how you have really vivid, this is pink, this pencil case is pink, but if I change the frequency or the wavelength of this color, it will change into maybe light pink, maybe something like that. You're changing the shade and the tones of the color by changing the wavelength. Okay? So this is what they're saying is called the red shift. Like in full, it's called the gravitational red shift. So we're calling it gravitational red shift. Okay, so red shift, blue shift, right? So if they are seeing that stars are turning or changing colors, are changing colors towards the red over time. This is over time, okay? So it's not that they're changing color. So that means that we are detecting color changes in these stars. So why do you think that is? Well, you know that is the frequency is decreasing because you're going towards the red shift. So we call it red shift. It's shifting towards red. So it's changing in frequency. So do you think that star then or us is moving away from each other or towards each other, if this is the observation that astronomers have observed? That stars out there are turning red over time. So then they said, okay, if it's turning red, then it's shifting towards the lower frequency. There is a decrease in frequency over time. And just remember, people are studying these for decades. Do you remember the person by the name of Tycho Brahe? Okay, that's how you pronounce Tycho Brahe. Some people might pronounce it that way. But he had data over 20 years. So this is what we observe. We look at stars. We have names of stars, right? We have named them. And we observe them over time, and they are shifting towards the red color. So then what does that mean? A shifting of red is a decrease in frequency. And what happens to a decrease in frequency in terms of energy level? What's happening to the energy level? Is it decreasing or increasing? What's the relationship between energy and frequency? It's exactly direct. It's a direct relationship. So an increase in frequency will also increase the energy level, right? Oh, sorry, an increase in frequency will increase the energy. So here's what we're observing. It's decreasing frequency, so the energy level is decreasing because of that red shift. So here's the question I'm asking you. Are stars moving away from each other or moving towards each other? A decrease in frequency. Decrease in frequency. Moving away, right? So this is the observation that they have for many, many years. So now we know that stars and galaxies themselves are collection of many, many stars, right? Our galaxy alone, the Milky Way galaxy, has billions and billions of stars. And every single star has at least one planet. So this is what we know now. Stars are moving away from each other. So galaxies are moving away from each other. So what can you say about the size of our galaxy? It's the size of not a galaxy itself, but the size of our universe. Is it getting bigger?
It's expanding.
The universe is expanding. And that is a proof, right? So the universe is expanding because of the Doppler effect that is happening with light. So when we observe that, the gravitational redshift, we summarize then that there is a decrease in frequency or a decrease in energy level. And the reason for that is because stars are moving away from each other, right? Not just stars. They said that galaxies are actually moving away from each other. So I'm running out of room here. So let's say here's our galaxy. There's this galaxy, and it has billions of stars in that galaxy alone. And that's not a big galaxy. It's a very big galaxy. On a scale of our universe, this is not as big as the other ones. There are bigger ones. But if you were to cross from our one end of our Milky Way to the other end, let's say straight path at the speed of light, which is the fastest you can get, right? Do you know how long it will take to do that? for the sunlight to go from the surface of the sun to the surface of the earth, it takes about 8.3 minutes. So the light that you're seeing out there, when you look at that and light hits you, okay, that's 8 minutes old. It had to go 8 minutes. It had to travel 8 minutes from the sun to earth, okay? Now if you're going from this end to the other end of our galaxy at the speed of light, it will take 100,000 years. That's huge. That is a big distance, right? So it's 100,000 light years away. Light years means that is the distance when you travel it at the speed of light, right? So 100,000 years. So if you were to just do a quick calculation here, let's say our galaxy, to go from end to end of our galaxy, I just said 100,000 years. So this is 100,000 light years, right? And what is the speed of light? 3 times 10 to the power of 8 meters per second. So if we were to use V equals D over T, what is the distance, the actual distance? Well, you're going to have your V, which we know, and you know the time, which is in years. But the problem is this is in meters per second. So let's convert. I'm going to get you guys to, and this will be a good review for the final exam as well, right? Because you're going to review your unit conversion now. So let's change this into seconds. That's going to be a lot of numbers. Let's see if your calculator can handle that, okay? Because we need to make sure that the units are uniform, right? So go ahead. I'm actually going to get you to convert years into seconds, and then you're going to be able to put this together because you're, look at this, meters per second, and then you have something in seconds, so you need to have that the same to cancel that seconds, right? And that will give you your meters. So go ahead, are you doing this now? So 100,000 years, how many seconds is that? Do you guys know how many seconds in 1 year? Okay, so years to days. So for days, let's do this one. Let's use 365.25. Okay, that's how many days you have in a year. So you gotta put that 0.25 there. Years are gone. Days. A lot of numbers. That's how many seconds? How many, you know how many seconds you have in a day? 86,400 seconds in 1 day, right? That's about how many times your heart beats in 1 day. 86,000 if your heart beats at 1 beat per second, so 60 beats per minute. Relaxed beat. Okay, so this is the time. Now you're going to multiply that by 3 times 10 to the power of 8. And let's see what you get. That is the distance, that is the size of our Milky Way. That's the diameter. And let's see if there is anything here actually tells us. Okay, so it actually is 1,700 light years. I only said 100,000 light years. It's actually more. So what is the diameter? What is the diameter? 9.5 times 10 to the power of 12 kilometer. 9.5 times 10 to the power of 17. Did we get that right?
Yeah, because we're in meters.
Oh, we're in meters. So it's a different weight.
I got 9.5 times 10 to the
20
Yeah.
in meters?
Yeah.
Yeah, that's gotta be it. 3.15576 exponent 12 times 3 exponent 8. Yeah, that's right. Yeah, so this is in meters, so in kilometers will be to the power of 17. That's right. So our answer matched what they said in on Google. Okay, so that's pretty close. So that is a very big universe, and so this is the conclusion that we came up with the Doppler effect of light, that stars are moving away from each other, galaxies are moving away from each other. We call it gravitational redshift. So therefore, the universe is expanding. Do you guys know what that means? Doesn't that blow your mind when I just told you that the universe is expanding? Okay, what does that mean? Does the universe have a wall? Does that have a boundary? And it's just getting bigger and bigger? What does that mean when we say the universe is expanding? This is something that I asked myself when I was in university. I go, well, how could scientists say that the universe is expanding? Does that make you ask that question? You should be wondering, right? Because if I tell you that this room is expanding, what does that mean? This room is expanding. That means the walls are moving away from us. So if I tell you that the universe is expanding, there are no walls. Our universe is just space. What that means when we say the universe is expanding is that whatever the light touches, okay, so that means that the light is actually spreading out. Because the stars, okay, whatever the sources of light there are in the universe, they're just moving away. Okay? So you have to remember that the standard paradigm that we subscribe to is that there was a Big Bang. And there was pitch black in the beginning, and there was this Big Bang. You can interpret it many ways you want. You could call it just the Big Bang or the creation, right? It doesn't matter. They all correspond to a Big Bang, the beginning of something. And then there was light. Okay? And then whatever that light is, it's kind of like this is pitch black, and you turn on a candle. And all of a sudden, that light started to spread out. And then it hit the wall and it started to reflect. And then we get some of that light back because we have walls, right? In the universe, there are no walls. So whatever the source of light was, it continues to get diffused. It continues to spread out. So it's still dark out there, but because it's going to take time for that light to spread out. So that's what we mean by the universe is expanding, because the objects itself are moving away from each other. So the light is actually getting spread out. So that's what we observe, the redshift. Okay, so how do we actually measure this Doppler effect? So let's quantify it. We can calculate what is happening. So we just said that the frequency is changing in Doppler effect, whereas it's not changing in refraction, right? So the Doppler effect for calculating the frequency, and I'm gonna call this one the F prime. So that would be the, I'll define this in a second here. So the old frequency, the actual frequency times V plus or minus V0, V plus or minus Vs. Okay, so there's a lot of letters here. So V is just the speed of sound. Okay? Whatever the speed of sound is. And it changes with temperature. So we can look into that as well, right? And then the V0, VO is the speed of the observer. So that would be you listening to that, or watching if it's light, right? The speed of the observer. The Vs is the speed of the source. So that could be the horn of the car, or that could be the car or the ambulance or whatever the source is, could be the speed of the source of light, the star. Okay, and F is the actual frequency, and F prime is the perceived Doppler frequency. Okay, all right, so we're gonna use that. Now, why is it plus and minus, you think? Plus means moving towards. So if it's moving towards you, you're gonna add it, and it's minus if it's moving away from you. So let's do one example. Okay, you got this one? All right, moving it up now? Okay. Okay, so let's do an example here. So let's say the speed of the source, let's say you have an ambulance and it's moving at, one of the students last year in my physics class, he's now a paramedic, and he came to visit just before Christmas time, and he told me that in the city, when they designed the city, there are actually firefighters or paramedic stations every 7 kilometers away. Did you guys know that? I did not know that. So when they're designing a city, they're 7 kilometers away. And then I say, why 7? And then we did this calculation so that they can get from their station to anywhere in the city within that 7 kilometer radius within 4 minutes time. So ideally, you want to get there for 4 minutes, someone having a heart attack, right? Because that's all you can take before you have brain death. Okay, that's interesting, I thought. So the VS, so let's say the speed of the source, the ambulance, and the speed is, let's say, 80 kilometers per hour. That's on average. That's how fast they will have to drive in the city. So you got to get out of the way of those ambulances because they're trying to save lives. Okay, so let's say the VS is 80 kilometers. Let's say you're just standing still. Let's say you actually stopped to make way for the ambulance and you are just sitting there. Okay, and let's say the frequency of the sound that you're hearing, let's just say 210 hertz. And the speed of sound, let's say it's a nice summer day and actually at 0 degrees, so let's say nice winter day, 331 meters per second. What is the Doppler frequency? Okay, so we get FV. Now let's say this is moving away from you. So then you'll go V minus VO divided by V minus VS. Okay, so that will give you the, okay, can you guys do that one? And let's see what is the perceived frequency. What happens to that 210 hertz? Now 80 kilometers per hour, we can't use that, right? So you're gonna have to divide this by 3.6. You guys remember that? Why I use 3.6? Unit conversion. You want a quick review? Okay, so you have 80, look at this, 80 kilometers per hour, right? So I put kilometers here, I put meters at the top, so 1,000 meters, 1 kilometer, there goes the kilometer. Now I gotta get rid of the hours into seconds, right? So hours there go away. 1 hour is how many seconds? 1 hour is 60 minutes, and 1 minute has 60 seconds. We can just go a shortcut here. 60 times 60 is 3,600, right? Now look at this. I'm going to simplify this, and I cut out the 2 here, take out the 2 there. So you have 80 times 10 over 36. What's 10 divided by 36? This is basically 1 over 3.6, isn't it? So then you go 80 times 1.1 over 3.6. So again, just a quick review. When you're going kilometers per hour to meters per second, you just divide that by 3.6. If you're going the other way around, you multiply it by 3.6 because of that unit conversion. It just makes it faster because we always use kilometers per hour, but we need meters per second. So at least know the conversion between these two. Okay, so you divide 80 by 3.6, and we have 22.2 repeating meters per second. So that's your source velocity, 22.2. Okay, so let's see what you get. And we have frequency of 225? Okay, so we get 225 hertz. That doesn't make sense.